Get it in the recording. Give y'all just one more minute. "15 seconds, just in case you haven't gotten it up yet. All right, locking answers here in 5, 4, 3, 2, and 1. Locking answers now. All right. What is the volume of this shape? You got a 1/3. Anyone else get anything different? I know people did get something different. What did you get, Malver? 2/3. Well, let's do it. So what am I integrating with respect to first? With respect to rho. Which means I need to figure out what is the antiderivative of rho squared with respect to rho. And that is what? Rho cubed over 3, and I evaluate that from 0 to 1. Which means it's 1 cubed over 3 minus 0 cubed over 3, or 1/3 sine d d theta. So then I have to go, okay, what's the antiderivative of sine of phi with respect to phi? What is it? Cosine. 1/3 times negative cosine. Be evaluated from 0 to 5. So when I plug in pi to cosine, what is that going to get? -1. But I'm considering negative cosine pi, which makes it a positive 1. Then I'll be subtracting the negative cosine of 0 or adding the cosine of 0. What was cosine of 0? Positive 1. Meaning that when I evaluate cosine from pi or 0 to pi, it's going to end up being a not negative 2. Positive 2. And then evaluate 2/3 from 0 to 1 with respect to theta. That integral, well, antiderivative of 2/3 with respect to theta is?
I mean,
Evaluate from 0 to 1, which makes it. Oh, dang it. All right. More importantly now, though, any questions? All right. So we're going to move away from integration just for a moment to introduce a new concept that we're going to start working with, both our derivatives and eventually integrations. Probably just be a day or two before we get back to integrations. Okay. So what we're going to talk about today whoops, I already did the daily quiz. That was habits, something called vector fields. So some of y'all who've gone through modern physics or taken modern physics, you've probably seen this somewhere or run into this at some point. If not, that's fine. We're going to discuss what they are. So what is a vector field? Let's first get the definition. So a vector field in R2, so in 2 dimensions, is an assignment of a 2-dimensional vector which we're going to do as a capital F. We're going to put that little half arrow notation above it to denote that it is a vector. If you look at your textbook, they use bold notation. Doesn't really work with bold notation here, so we're going to just make sure that we do a vector. To each point in the XY plane on some domain, really. So each point, x, y, that's in some domain D, which is in R2. That domain D could potentially be all of R2, so the XY plane, but we're going to be a little bit conservative with how we define it and just say it doesn't have to be all of R2, it could just be some part of R2. That subset D is called the domain of the vector field. So 1 second, I wonder if I can get this picture up here. Nope, too big. I'll have to leave it on the next page. So just a quick example of what vector fields look like. You've seen them in plenty of places. So depending on where I am at, I'm heading in a direction at a certain magnitude. And so nice easy one, technically if we're looking at gravitational pull on Earth and Moon, how they relate to each other, there's 3 dimensions, not 2 dimensions, but keep it simple, we get a 2-dimensional image. I know, okay, well, if I'm anywhere over here, I'll probably be approaching the moon first. I have all my gravity pulling me. If I'm somewhere up in here, I'm going to get pulled to a larger mass, which is the Earth. And I can see, okay, when I'm far away, I'm getting pulled very slightly, but then the closer I get, the harder and harder I get pulled. Okay? So depending on where I'm at with relationship to the moon and Earth, then I'm going to be being pulled in some direction with some sort of magnitude. And it doesn't just matter with gravitational. So another great way is water flowing through a river or some other estuary and it's going around a rock. So you have where the water is flowing and at what speed. It's going to be different speeds depending on where you're at. And then as it comes in contact with an object, it's going to be diverting one way or the other. You might slow down, you might speed up, or it might be the same way. And then you can kind of get some of this craziness that occurs afterwards, which makes a lot of, there's a pain in the butt to calculate numerically. Can just say that. So this is what vector fields look like, right? Every point in this domain where you just assign a vector, each vector is going to have its own different magnitude and direction. So question is, how do we represent this? So, oh, I wanted to make this note. In 3 dimensions, pretty similar definition. My vector field, depending on my position, three-dimensional vector to each point. X, Y, Z in some domain that is a subset of 3 dimensions. So I'm going to start dropping this of X and Y just for a moment. We'll see it in both cases, but there's 2 main ways that we choose to represent these vector fields. Okay. One is going to be component wise. We're going to list it out as a vector on paper. The other one's using those unit vectors I, J, and K, or I and J for just working in 2 dimensions. So first up, if I'm working in 2-dimensional space, my vector field, well, in the first component, in the X dimension, it's determined by some function of X or Y. So how far I'm traveling in the X direction depends upon where I'm at in the X and Y axis. And then also in a different manner, my magnitude in the Y direction is going to be dependent upon where I'm at on the XY plane or somewhere in R2. Or you can be representing it as this function P times that unit vector I. So saying going in the first dimension plus Q times J. And if we go to 3 dimensions, we're essentially going to stick with the same 2 styles, right? I build it component wise where I see the function for the X direction. That's going to determine how much I travel in the X direction, how much I travel in the Y direction, and then how much I travel in the Z direction. Or the same little unit vector notation. J plus R, X, Y, Z times a unit vector K. And I can tell just even based off of this first image for where we're dealing with kind of gravitational forces around Earth and Moon, depending on where I'm at, if we're just considering this two-dimensional space, I can see that I don't have a constant function here, right? I don't have a constant way in which these vectors are changing. It depends on where I'm at. So I'm going to have some more complicated functions and determine how much I change in the x direction, how much I go in the y direction, depending on that relationship for each of these dimensions. So all that being said, that Newton's law of gravitation can be represented as a vector field. So if you're considering a vector, Newton's gravitational law compared for two masses that are side by side in space, it's his gravitational constant times the mass of the two objects divided by distance between them. Times vector xyz over r. So in this first component is that function p of x comma y comma z, which just says, hey, I'm going to take where you're at in the x dimension, divide it by the distance between these two objects. And that's going to determine your vector, how much you're being pulled in the x direction towards these masses. I do a similar thing for y and z. So this is just a vector field. And again, depending on what you're at, where you're at, you can determine which way you're getting pulled. So just any quick questions right now, what the idea is of a vector field. What do you got for me?
Visual presentation of the way all elements interact with objects.
For, I mean, it depends on what you're talking about. I'm giving you a specific example for how the gravitational fields for two masses in this one. Vector fields are just vector fields. You assign a vector to a point. What their purpose is situational. Any other questions? All right, well, let's get used to using some of this. So first thing I want you to do, what was that? Make sure that negative is apparent there. So we're going to sketch 4 points or 4 vectors in this vector field defined by the vector negative 2x times 2y. So I need to get 4 points, and then from those 4 points, figure out what the vector looks like at those 4 points. So in the XY plane, someone give me 4 points, relatively close to the origin. Don't go too crazy on your values. 1, 2, what else? Negative 1 what? Negative 1, 1. All right, need 2 more. What was that? 2 and negative 1? 2, negative 1, and then let's do. And that way we'll hit all 4 quadrants. First quadrant, second quadrant, fourth quadrant, third quadrant. Yeah, that way we'll hit all 4 quadrants. So for the point 1, 2, what is my vector going to be? So I'm going to take negative 2, multiply it by the x coordinate for that point. And take 2, multiply it by the y coordinate. So the x coordinate for this first point is 1. So the first component of my vector is going to be a negative 2 times 1, giving me negative 2. And then what about the y component of this vector? What is it going to be? 4. Because I take the 2 from my y value, multiply it by the 2 that I'm getting from how I determine my vector field. It's going to be a 4. So it's pointing negative 2 in the x direction and 4 up in the y direction. All right, what about the point negative 1, 1? Two, 2. I take the x coordinate, multiply it by negative 2. So negative 2 times negative 1 gives me positive 2. And then 2 times a positive 1 for the y coordinate gives me a positive 2 again. What about 2, negative 1? What's its vector going to be? Negative 4, negative 2. What about the vector for the point negative 1, negative 1? All right, so let's sketch it. X-axis, my y-axis. 1, 2, 3, 4, 4, 5. 2, 3, 4. Roughly evenly spaced. So I'm going to go through and mark all my points. I had 1, 2. I had negative 1, 1. I have 2, negative 1. And then I have 2, negative 1, then negative 1, 1. Or I said negative 1, 1, negative 1, negative 1. Then each of these points has a vector. For the point 1, 2, its vector was negative 2, 4. So it's going to be pointing negative 2 to the left and then 4 up. 1, 2, 3, 4. It's pointing to the left and 4 up from that point. 1, 2. So it's got a really strong push up to the northwest. That's the way we can say it. All right, what about negative 1, 1? What's this vector looking like? 2, 2. So I go how many in the next direction? To the right, 2 up. That's going to give me my magnitude. Two, 2 from the point. Negative 1, 1. What about for 2, negative 1? What's up? No, because that vector is coming from what point? So we got this vector 2, 2 from realizing that we're calculating at what point? -1, 1. So emanating from this point, where am I heading and how fast? Well, it's determined by this vector 2, 2. So I'm heading in this direction, not as fast as I would be for this first one, right? But I'm still heading out in a pretty fast way. I've got a good amount of magnitude in this direction. Don't matter, because every point you get, you're going to get a vector. Right? It doesn't necessarily matter what order I go through these. It's just top to bottom from the list that we made. All right, what about at 2, -1? What's my vector? -4, -2, which means I'm traveling to the left on the x-axis 4 units, and then down on the y-axis, how many units? 2. So another strong little vector. 1, 2, 3, 4. And then last point, at -1, -1, where is that vector heading? So you go to the right and 2 down. And if I wanted to get a more detailed depiction of what's kind of happening here, I would just calculate more points and look at their vectors. If I was anywhere on the y-axis, where would my vectors be at? On the y-axis. Think about this relationship right here. If I was on the y-axis, where would my vectors be at? Well, if I'm anywhere up here, right, my x value is what? 0. My y value is, on this part of the line, positive. So take a -2 multiplied by 0, it's going to be a 0. Which means if I'm on the y-axis, I'm not going to be traveling anywhere in the x direction. If I take a +2 multiplied by a positive number, it's going to be what? Positive. Which means those vectors aren't going off the y-axis, but they are going one direction. Up. So all my other vectors, no matter where they are up. And then the farther away that I get from the origin, the stronger those vectors are pointing upwards. Because I'm always multiplying it by 2. What if I was on the lower half of the y-axis? Negative y values, which means all my vectors are going to be pointing where? Down. So if I'm above the x-axis, my vectors are always pointing up. If I'm below the x-axis, the vectors are always pointing down. So I get this vector field of I'm always pointing upwards or downwards. But then also look at what happens in the x direction. Well, if I have to the right of, if I'm on the, let's say on the x-axis. On the x-axis, that means my y value is what? 0. So I'm not going to be going off the x-axis. I gain no height. If I have positive x values, what direction will that vector be heading? Opposite direction to the left. I'm going to take some positive value, multiply it by what? 2, which means it's going to have a negative component in the x direction, which means anywhere over here, my vectors are always pointing to the left. That's what we saw. Even up here at 0.12, it's a positive x value in the x direction. Which way did that vector point? Left. I had negative or 2 -1. X value is positive here. Which direction did that vector point? The left. For 1, 2, it is above the x-axis. On the y direction, where did it point? Up. -1 on the y-axis, where this vector also points. Yeah. So I get left and down, left and up. If I'm on the negative side of the x-axis, then multiplying it by -2, that means the x values are going to be traveling in the positive direction. So I get a vector going to the right if I'm the negative x-axis, and then up if I'm in the positive y. So all my vectors, no matter where I'm at, will be pointing up and to the right if I'm in that second quadrant. They're going to get larger and larger and larger. And then I can kind of just fill out a rough sketch of what's happening anywhere else. In this case, all these vectors are pushing me towards the y-axis or pushing me towards the y-axis and away from the x-axis if I'm not already on the x-axis. So you get this idea of a way to sketch what's happening and where things are going. So no matter where you start out with respect to the y-axis, you're going to be moving towards it. If you're with respect to the x-axis, you're always moving away from it unless you got unlucky and we're already starting on the x-axis. And every single one of you is in differential equations. What does this look like? Studied at the very beginning of the semester. Slope fields, right? Where you determine equilibrium, how things are changing. Slope fields are just vector fields. Yeah. Oh, really? X. Yep. So if this was how your vector field is determined, yeah, you just go through this same process of just plugging in points to figure out where the vectors are pointing.
And if
Yeah. Nope, it'll be completely different. Because how far you're traveling in the x direction now depends upon what? Your y value. How far you travel in the y direction now depends on x value. Whereas before, that first example I gave you is split. There'd be a somewhat symmetrical shape to that vector field, but it would create two different vectors.
okay, so if we use the formula for 1 and 2, so we substitute the 1 for the x, right?
Yep.
And so that would be
Let's do a blue. If we did 1, 2, it'd be
that would be the same.
be 1, 1/2. So for this first vector, I'd only be increasing the x direction by value of 1/2, y up by 1. The two vectors have the same magnitude, but they're pointing in slightly different directions. So yeah, the main point is just you have to point each other, right? How many points can I plug in? How many calculations do I do? And how many little arrows do I draw? How do you determine what?
The speed.
The speed? What is it for vectors? That's just your magnitude, because speed is velocity without direction. So it's just the magnitude of the vector.
Like on visual, on the.
Like, how do I do that? I just plotted a bunch of points in my head and then realized what's happening. Anytime I have positive x and y values, are going to be the outcome for all my vectors. Take positive x and positive y. If I take positive x multiplied by -2, it's going to be a positive number or negative number. Negative. So all the vectors in that first quadrant are going to be pointing to the left. And since I'm taking a positive y, multiplying it by 2, it's still what? Positive. So everything over here in this quadrant is going to be going to the left and up. So we're going to get some varying angle here. Granted, since it's a constant multiple of 2, all of these are going to have a rough slope of 2. You're going to see a bunch of parallel lines. Come down here in the fourth quadrant. Negative x values, positive x values, negative y values, which means all my vector components are going to be negative and negative. Left and left. I'm in second quadrant. Negative x values, positive y values. What direction will all my vectors be pointing? The right? No. Because negative times negative is positive. Positive times positive is still positive. And then last one, quadrant 3, to the right and down, because we're going to get positive x component, but then a negative y component.
I understand how it works. And you mentioned something about 4 away from the origin. Really?
Well, because what am I doing to all the x and y values? I'm multiplying them by what to get my vectors? Negative 2 and positive 2. So whether or not I'm changing the direction, I'm just multiplying by 2. So for the point 1, 1, or let's even say negative 1, 1, it was a vector of positive 2, negative 2. What if I did negative 5, negative 5? Well, it's vector B. Negative 10. So now it's going to be traveling positive 10 units in the x direction and negative 10 units in the y direction, which is going to be, has much more magnitude than 2, negative 2. In fact, by a multiple of 5.
So then the longer the line,
The harder you're getting pulled in that direction. And in intermediate calculation, you'll learn how to make these. Usually when you pick this, you do unit vectors, so you won't have all these crazy overlapping lines or something even smaller, but then use a color or something to denote the magnitude of all of those. All right, what other questions? Okay. So one of the reasons in calculus we study vector fields, and one of the reasons why we care about vector fields in general is because of something called gradient fields. And depending on what really area of physics or mechanics you're working in, sometimes these are also referred to as conservation fields. So these vector fields are extremely important to physics. Because they are used to model physical systems in which energy is conserved. And they're going to be called gradient fields because what calculus tool do you think we're going to use when grading these? The gradients, which is kind of your vector of all of your partial derivatives. So just want a real quick recap. for any function f, let's say that's two-dimensional, then the gradient of f is a vector, wherein the x component of this vector is what partial of this function? What partial? The partial of x is in the x component of this vector, and the partial of y is in the y component. That's what the gradient was. If it was in 3 dimensions, then how many entries do I have in my gradient for this function? 3. And each dimension is the gradient in that direction. Or I said gradient, the partial in that direction. So just that quick reminder, because then we have another definition. Not only defining a vector field today, we're also going to define what it means to be a gradient field. So it doesn't matter whether or not you're working in 2 dimensions or 3 dimensions. A vector field in R3 is a gradient field. If there exists a scalar function f such that the gradient of this little f is equal to that vector field. Because the gradient of f is how I'm determining all those vectors depending on where I'm at in my space, whether it be 2 dimensions or 3 dimensions. That function little f that we have to take the gradient of to get this gradient field is often called the potential function. Of my vector field f. So in just a slightly easy example, just to demonstrate the idea of what this is. One vector field is the gradient field of the potential function f of x comma y comma z equal to x squared times cosine of yz plus y squared z squared. Essentially, what is the gradient field created from this potential function? Which means I need to find the gradient of this function f, which means I need to find what, and what. All the partials, right? Partial with respect to x, partial with respect to y, and partial with respect to z. So yeah, you still got to remember how to do all of your little derivatives and quickly. So what's the partial with respect to x going to be? Well, just like with integration, if I'm taking the derivative with respect to x, I hold what and what constant? Y and z. So I have an x squared times a cosine of yz. So cosine of yz is considered a what? Constant. So it's just the derivative of x squared times a constant plus the derivative of y squared z squared. And y squared z squared is just a constant. So split the derivative up into two parts. Well, let's do the easier part first. Derivative of a constant is always what? 0. So this term is going to disappear. Now I just got to figure out what's the derivative of x squared times a constant. Well, what's the derivative of x squared? 2x. So the derivative of x squared times a constant is 2x times a constant. So someone tell me then, what is the partial with respect to x going to be? Cosine of yz. That's the partial with respect to x. What about my partial with respect to y? Well, if I'm taking the partial with respect to y, I take the derivative with respect to y while holding what constant? X and z. So I have an x squared times a cosine of yz, and then I'm going to be adding it to whatever the derivative is of y squared times z squared. That's split by an addition, so I get to split that in my head. I get to choose which part do I want to do first. Right side, it's a little bit easier, right? Because that's y squared times the constant, and derivative of y squared is what? 2y. So that second part after the plus just becomes a 2y times z squared. And I'm just going to leave myself room so I can fill in the rest later. And if I need to erase and move it over, I can. So then I have to figure out, okay, what is the derivative of x squared times cosine of yz? I'll take the derivative with respect to y, which means x squared again is constant. So this is derivative of a constant times cosine of a function of y. So I just need to figure out what this derivative is, multiplied by x squared later. So what is the derivative of cosine times a constant? So I take the derivative of the outer part, using chain rule. So derivative of cosine is negative sine. So I have my x squared times negative sine, leave alone what's inside. And then I make sure I multiply by the derivative of the inside. What is the derivative of y times z with respect to y? Just be z. Y times a constant, its derivative is just that constant. So that's going to become a negative x squared times a z times sine of yz plus 2 times yz squared. How are we feeling? Don't be afraid to say not good. It's supposed to be a little bit of review for those partials. We're gonna have to kickstart it back into full gear like we were doing it earlier. Or like how we were doing it earlier. All right, last one. You need to take the partial with respect to z. Perfect. Because really, when I consider cosine of yz's derivative, it was just derivative of the outside, which gave me my negative sign, repeat the inside, but then I need to multiply by the derivative with respect to z this time, which is going to be y. So that's where I get this y from instead of the z from before. I still have this negative x squared, the negative coming from the sign, x squared from being there before. Then I look at take y squared times z squared, take the derivative with respect to z, that's going to be a 2z times y squared. So then, what does this vector field look like? So my vector field Well, in the x direction, how I'm traveling in the x directions dependent upon 2 times x coordinate times cosine of the y coordinate and z coordinate. And then I have how I travel in the y direction. Negative x squared z sine of yz plus 2yz squared. Now I travel in the z direction. It's based on negative x squared y times sine of x times y plus 2z y squared. So that right there is my gradient field for this function f. Is it really 153 already? Oh, wow. No, wrong way. That's what I want to do. So any questions for me? So we're going to talk about on Wednesday what it means to be a conservative vector field. But then what you're going to see is that this is just going to create a new space, and it's going to create a new space for us to integrate it. Right? Because if we're especially thinking in 3 dimensions, I don't just have my position in 3 dimensions, I also have a direction, how fast I'm usually traveling in those 3 dimensions. So I still might want to integrate over that entire field, figure out, okay, what is for over this entire vector field, what is the volume or average or area or anything like that. And you can have some physics interpretations to those calculations. Okay, so we're going to start. This is building up the space, so then we can start doing the calculus to the space. All right. Has everyone got this written down? I didn't actually do this. Let's see what it looks like. If you want to take a break and just step out for DiffyQ, you're more than welcome to. I'm not going to be offended. I know they have vector field. Was it 2x x times cosine of y times z? X times z times sine of y times z. Times z squared. It's probably going to be something crazy. I'm going to regret doing this. That is not what it should look like. There we go. Scale them down. There we go. That's a rough shape, a rough idea of what's happening in 3D with that vector field. So we're going to see the farther away we get from the origin, we kind of start shooting off into corners. Zoom out a little bit more. We see something similar where, okay, there's even some vectors that are looks like they're pointing off here. That didn't really help me at all. Let's scale this by 15. Try to declutter it a little bit. Yeah. It's a pretty interesting vector field, kind of making an X. Yeah. Oh, I was just recording on that. I guess let me put it in the recording since I was doing that. Here's me playing around with that vector field again. All right. Yeah. Make sure you take that little break before Diffie Q. If you need a nap, go ahead and take a nap. Hey, you're welcome to leave whenever. Though you probably want to talk with your work about scheduling you during class. Because let me end this real quick.